Hi, everyone, and welcome to our presentation. As Rich said, my name is Miguel, and together with my partner, Calli, we're going to present our thesis titled Enhancing Flutter-Foil Energy Generation. Our advisor is Professor Royce. Before I begin, I'd like to go over some acknowledgments. We'd like to thank Professor Royce for all of his knowledge and expertise throughout this process, Professors Gallagher and Lutz for acting as our reader and editor, respectively, Professor Martin for his assistance on the electrical engineering portions of our thesis, Pat Doherty for maintaining the flow channel for us, and all of our various schoolmates who have come to our aid throughout this whole project. So I'm going to start out with a brief outline. I'm going to go over the objectives of the thesis and then move into the background, theory, foil design, construction procedure, and testing methodology. Will is then going to take over and discuss our results, conclusions, a couple challenges, and recommendations for future work. Our objectives were threefold. First, we wanted to verify that power generation is possible using vortex-induced vibrations through the design and construction of a power takeoff mechanism. Second, we wanted to examine the effects of pitch stiffness in the foil itself on power generation. And finally, we wanted to improve the VIV testing capabilities here at Webb through the design and construction of a new testing apparatus. So before I get into all the nitty-gritty, what's the point? Why do we care about this? Vortex-induced vibrations are normally seen as a bad thing, and the offshore industry specifically has conducted a lot of research into how to prevent VIV. This is because it can cause damage to immersed structures. For oil, this can be oil risers or drills, but it can also happen to land-based structures such as bridges, power lines, and towers. However, because it is a completely naturally occurring process that takes energy out of the environment, it has potential for use as a way to generate clean power. So, as I mentioned, vortex-induced vibrations are a naturally occurring process that have been observed since at least the 16th century. They occur when bluff bodies are immersed in a free stream flow, bluff body being when the pressure drag will dominate over the frictional drag. Vortices will form off the trailing edge of these objects, which can then cause vibration. This is known as vortex shedding. Here's a little animation of a cylindrical body experiencing vortex-induced vibrations. The formation and severity of VIV is dependent on the Reynolds number of the body. The Reynolds number is a non-dimensional term relating the inertial and viscous forces of the body, and it is given by this equation, where ρ is the fluid density, u is the relative speed, L is the characteristic length, in this case the chord length of our foil, and mu is the viscosity. So a little background fluid theory. For inviscid flow, the viscosity is assumed zero, and fluid streamlines will follow the shape of a submerged object, which can be seen above. However, as we all know, water does have a viscosity. In viscous flow, a boundary layer forms around the object. At low Reynolds numbers, the fluid behavior follows inviscid theory, and the streamlines will still look like that. As Reynolds number increases, separation will start to occur and create low pressure zones behind the object, which can be seen in the red box. At higher Reynolds numbers, these vortices start to form on alternating sides of the body, creating what is known as a von Karman vortex street. This whole process is known as vortex shedding. Let me admit Will's stat. Another important aspect is the Struhal number, which is a non-dimensional term relating the unsteady and inertial forces of the body, and it is given by this equation, where Fv is the frequency of vortex shedding, L is the chord length of the foil, and U is the relative speed. Experimental data has shown that vortex shedding occurs at a small range of Struhal numbers centered around 0.21. In the graph above, the x-axis is Reynolds number, the y-axis is Struhal number, and the plot shows Struhal numbers at which VIV occurred. You can see that for a large range of Reynolds numbers, the plot centers around that Struhal number of 0.21. Using this relationship, we can predict the frequency of vortex-induced vibrations for any given geometry and flow speed. So a large part of our thesis centered around our foils. The vortices created by vortex shedding created forces on the foil itself, which allowed it to oscillate. These forces were, number one, lift, which were the forces on the body perpendicular to the direction of flow. Lift is a function of the fluid density and frontal area, and it is given by this equation, where Cl is the lift coefficient, ρ is the density, u is the relative speed, and A is the frontal area. Drag is the force on the body parallel to the direction of flow. It is also a function of density and frontal area, and it is given by the equation above, where CD is the drag coefficient, and rho, u, and a are the same values as in the lift equation. A major part of our thesis centered around generating power. We generated power by turning the rotor of an induction generator mechanically using the heaving action of our foil. This was done using a rack and pinion type connector, an animation of which can be seen here. This motion then created an induced current, which created a rotating magnetic field. This allowed a voltage potential to be created, which was then taken off the system and into a circuit. Our thesis is a continuation of several previous research projects, the first of which was the Vivace converter, which stands for vortex-induced vibration for aquatic clean energy. This was created at the University of Michigan by Dr. Michael Bernices in 2006. The picture above is the Vivace converter being lowered into the St. Clair River. Note the use of cylindrical foils. There are also a number of previous Webb theses that have been conducted on this topic. This started in 2008 with Lindsay Burns' thesis, where she explored the use of faired fat foils in place of the cylinders and found that she could increase the amplitudes of oscillation by up to 2 times. This was continued in 2017 by Zinval, Gargiulo, and Lawson, 2018 by Gagliardi and McReal, and 2023 by Mathis and Sullivan, who all attempted to optimize amplitudes of oscillation by varying heave stiffnesses, pivot points, pitch stiffnesses, and foil sections. So how did we design all these different foils that we're using? We had specifically 3 different foils. The first was a cylinder with a 1.19-inch radius, which can be seen above. The second was a fat foil, where just a faired section was added to the end of that cylinder. And finally, the same fat foil, but with an added pitch stiffness element. The reason we had 3 different foils was so we could compare their heaving motion. By comparing the heaving motion of the fat foils with the cylinder, we could compare our data to that previously collected specifically by Lindsay Burns in 2008 and validate our new apparatus. In addition, we could also compare the power output, since power output is proportional to the heave amplitude. For our device, our foils were constrained. They were only free to move in heave and pitch, as can be seen here. They pitch about the elastic center of the foil, and the lift forces act at the aerodynamic center. The difference in these 2 locations allowed for flutter instability in the foil, which meant that the foil pitched freely while in motion. The drag forces on the foil were neglected due to constraints in the direction of flow. We also used springs to induce restorative forces in number 1, heave. This is so we could achieve resonance between the frequency of VIV and the natural frequency of the system. The ideal flow speed at which this occurred can be given by this equation here, where 0.21 stands in for the ideal Struhal number, C is the chord length of the foil, KEQ is the equivalent spring constant of the entire system, M foil is the mass of the foil slider, and M added is the added mass from the foil moving through water. We also added restorative forces in pitch, again to achieve resonance between the pitch natural frequency of the foil, the heave natural frequency, and the frequency of VIV. The whole point of this was to adjust the torsional stiffness as closely match the heave natural frequency as close as possible. So I mentioned we built a new apparatus for this. This was done in 3 separate parts, the first of which was the aluminum frame. This was constructed out of 1.5-inch 80-20 aluminum extrusion bar, and this is what tied together the plexiglass insert, the foil slider, to the main body of the flow channel. The foil carriage was constructed out of 1.25 outer diameter inch carbon fiber tubing and connected at the joints by 3D printed brackets. This entire part is what slides up and down in our system. Finally, the circulating water channel insert was created out of plexiglass. This was designed to direct flow over the submerged portions of the aluminum frame and ensure smooth, even flow over the foil itself. Here's a little video of our plexiglass panels being cut on Webb's ShopBot. And here is a model of the overall assembly. So I talked about the foil design. This is how we constructed it. It was constructed in 3 parts. First, the PVC core, to which we added 3D printed fairings and 3D printed end caps. The little arms off the trailing edge were so we could induce torsional stiffness to the foil. So now that we've gone over the construction, we needed 2 different data sets in order to achieve our objectives. The first was that we needed to collect heave amplitude data. This is so we could validate our new apparatus against previous data, namely Lindsay Burns 2008 data, and so we can compare the effects of the foil section and the pitch stiffened foil. Second, we needed to collect voltage data. By measuring the output voltage and therefore power of the device, we can compare this to our theoretical model and to the power takeoff data from the Vivace study in order to determine the effectiveness of our power takeoff system. In order to complete any testing, we needed to know the flow conditions in the flow channel. In order to correctly induce VIV, you need to be able to control the flow velocity. The flow channel has a motor, which is connected to a variable frequency drive. The motor has a speed in RPM, which can be controlled by changing the speed of the VFD in Hertz. The flow itself was measured by a pitot tube and manometer using the Bernoulli equation to arrive at a velocity. This is a diagram of the flow speed mapping done this year by Richard Stephen Thill II, in which the x-axis is the VFD speed in Hertz, the y-axis is the flow speed in feet per second. The large blue dots are individually mapped data points, and the small dotted blue line is a linear regression connecting them. The R-squared value of the fit line is 0.99, indicating a very high correlation. We measured the heave amplitude using a rotary encoder. This was connected to our foil via another rack and pinion that heaved with the foil. The rotary motion then gave a voltage output, which was sent to our signal conditioner software, LabVIEW. This software took the voltage output and turned it into usable amplitude data, a diagram of which can be seen above. This data was then run through a fast Fourier transform in Excel in order to identify the frequencies and max heave amplitudes. This data was then non-dimensionalized to compare with previous research. First, with the non-dimensionalized heave amplitude, A star, where Y is a measured heave amplitude and D is the vertical foil thickness, in this case, the foil diameter. U star is a non-dimensionalized flow speed, in which U is again a measured flow speed, D is the foil thickness, and Fn is the natural frequency of the system. We measured voltage using a direct current generator, again connected by a rack and pinion power takeoff system, which can be seen above. This was connected to a known circuit. The output of the known circuit was then connected to a National Instruments MIDAC, which allowed us to record the voltage data over time. The power was then calculated using Ohm's law. In the equation above, V is the voltage output we measured, and R is the resistance of the known circuit. So we have all these different variables, which means we had to have a large comprehensive test matrix, an example of which can be seen here. This test matrix allowed us to step through each of the variables in a coordinated manner, starting with the foil type, spring constant, flow speed, and whether or not we had the resistive generator load applied. In the final column, you can see that we noted whether or not the foil self-excited. In some of the higher speed tests, the foil did self-excite, and in a lot of tests, we had to get it started. I would now like to invite Will up to discuss our results.
Thank you, Miguel. Motions did occur at many of our expected natural frequencies, and the motions for the cylinder look like this.
We were very excited to see that for the first time.
Self-excitation, as Miguel mentioned, did occur for several of our runs, and this was a very good sign as it indicated a very low friction present in the system, which allowed us to get good data out. The heaving motions, as shown on the graph above, where the x-axis is at time in seconds, and the y-axis is the amplitude of oscillation in inches, shows a very sinusoidal motion, as expected, with a nearly 1.47-inch average amplitude and a half-second period. That half-second period will be consistent throughout all of our foils. We also observed a beating frequency. This indicates that while we could get very close to the natural resonant frequency of the system, due to the conditions through which we could step the variable frequency drive, we couldn't nail it exactly. So some small beating is going to be present within the system. To validate our apparatus data, we had to compare it with Burns 2008 non-dimensionalized cylinder data, which can be seen here. On the x-axis is our non-dimensionalized flow velocity, U star, and on the y-axis is our non-dimensionalized heave amplitude, A star. Our data is shown in the triangle and the diamond points, which are very close to Burns's data. This indicates that we are within an acceptable operating range, and therefore our apparatus is operating as expected with little added friction. For each of our tests, we conducted a fast Fourier transform to identify the frequencies at play in our system. The x-axis of the fast Fourier transform is the frequency in Hertz. and the y-axis is the magnitude of the fast Fourier transform itself, which is non-dimensional. We can identify from this data that the natural frequency for the cylinder oscillating with a heave stiffness of 4.296 pounds-force per inch is 2.25 hertz. From our theoretical calculations, which Miguel described earlier, we have calculated a natural frequency for this condition of 2.19 hertz. With a 2.7% difference, we are confident that our calculations are correct and use them to proceed through the rest of our testing program. This fast Fourier transform also helps us to identify beating frequencies at play in the system, which can be seen in some of the smaller spikes present around a single large one. For the actual fat foil itself, we were again very excited to see flutter happen. I will show you now one of our smaller oscillations so that you can see the motions at play. We did experience a very high amplitude of oscillations here, almost worryingly so. A video is playing now. This actually required apparatus modifications to be made to account for the significantly increased amplitudes, which we were not expecting, which we were very, very excited to see. For the heaving motions themselves, for the fat foil, we can again see our graph, sinusoidal motion, with the x-axis being time in seconds and the y-axis being the amplitude in inches. For the fat foil, we experienced an average amplitude of 3.36 inches, with a 129% increase over the baseline cylinder condition. And again, the half-second period was present. Less beating was observed at the more efficient foil and the higher speeds. For the fat foil with added pitch stiffness, we again achieved flutter, and the motions can be seen here. We did see less amplitude than the free fluttering foil. However, we were unable to achieve direct resonance with the heave and the pitch stiffness. This is likely responsible for the amplitude reduction. The torsional system does require some redesign, as we were unable to get our speeds and our torsional stiffness to exactly match the resonance. And in fact, when we got close, we had over-stiffened the torsional system, which actually negated all of our motion. The heaving motions of this system, when we did get it operating, were again sinusoidal. The same type of graph can be seen above, with the x-axis in seconds and the y-axis as amplitude in inches, and a 2.53 inch amplitude can be seen. This is a 73% increase over the cylinder. Not quite as good as the free fluttering foil, but still much better. And again, our half-second period is present. Some beating was observed in this system, and this is likely due to the increased damping due to not being in perfect resonance in our pitch stiffness. To compare the foil types, the graph is shown above, where the y-axis is the non-dimensionalized amplitude, A star, and the x-axis is the spring stiffness, pounds-force per inch. We tested each of our foils at 2 consistent spring constants, so you can see them displayed here. The free fluttering fat foil, shown in orange or the triangle data set, had the greatest amplitudes, over double the cylinder amplitudes. The pitch stiffened foil improved upon the cylinder amplitudes, but was not as good, likely due to being unable to come into complete resonance, as mentioned before. And furthermore, the pitch stiffened foil showed the greatest amplitude increase at higher speed relative to the lower speed tested. The power takeoff was validated first with qualitative observations. Lights were powered by the oscillations and can be seen in the red circle above. We also observed that the loaded generator damping did have a visible effect on our heave amplitudes. I'll talk about that a bit now. The graph above shows the amplitude on the y-axis in inches and the x-axis is time in seconds. The blue circular data set shows the unloaded amplitude, that is, the amplitude of oscillations when the generator does not have a resistive load connected, and the orange or square data set shows the loaded amplitude when a resistive load is connected to the generator. It can be seen that for the cylinder with our low spring stiffness condition, the loaded amplitude is smaller by about 7% than the unloaded condition. This effect, however, is reduced at higher speeds with more effective foil shapes, such as our fat foil shown here. Here, the unloaded and loaded amplitudes are nearly identical. Additionally, when the generator is loaded, as can be seen in the data set above, where time is again on the x-axis in seconds and the y-axis is again amplitude in inches, beating is increased. This is because damping is introduced by the torque
added by the generator when loaded, and therefore the system is pushed further out of its resonance, away from its natural frequency. Therefore, the beating frequency is increased. To calculate the theoretical power output of the system, we took the average energy of the system to be the maximum potential spring energy. This is because in a simple harmonic system, the potential energy and kinetic energy oscillate between one another, and at the maximum excursion, or the maximum amplitude of oscillation, the entire energy in the system can be assumed to be the potential energy, as there's no kinetic energy at the ends of its motion. To find power, we integrate over one period of the sine wave, using the equation shown above, where PE is the potential energy of the spring system, omega is the angular velocity, lowercase t is time in seconds, and capital T is the period of oscillations, that half second shown in all of our previous data. The power was calculated for each foil at each flow speed and can be seen above. For our fat foil in our high stiffness and high speed condition, we calculated a theoretical power output of 17.25 watts. To measure our power output, we measured the voltage drop across our resistive load using the voltage measured by our system, shown on the graph here. The x-axis is again time, seconds, and the y-axis is voltage in volts. Here, a 675 ohm resistor load was added, and our 2.9 volt output was measured at the peaks. The power across this, using Ohm's law, is 12.5 milliwatts. To calculate our extracted power, we took our measured power in the numerator and our theoretical power in the denominator, and got a power extracted from the system of 0.07%. I'm aware that that is an alarming number. However, our generator was significantly undersized for this application. It was in fact operating at its maximum output for this RPM and due to its own construction limitations. Impacts on heave were, however, more apparent when a greater percent of the power was extracted from the system. So for the cylinder condition, where 0.42 and 0.34% of the power was extracted, we actually did see increased beating as more of that energy was extracted and the oscillations were further dampened. To conclude our presentation, we were able to validate our new apparatus with cylinder and fat foil tests against our previous 2008 data. Additionally, we confirmed that voltage could be generated by our heaving foil and that power can be taken off of the system. This does indicate that this type of technology is viable for blue water deployment when scaled and designed properly. For future work, we recommend upgrading the apparatus with a linear sliding system, as the current design has small amounts of induced friction and play. We also recommend optimizing the pitch stiffness to achieve proper resonance, which we were unable to do so far. Furthermore, we recommend developing the power takeoff with a feedback loop to automatically optimize the stiffnesses for the flow speed and the damping due to the generator load, so that the system is always outputting at its maximum possible amplitudes with the best possible resonance. We also recommend eliminating the dead zones at the peaks and troughs of our motion. At this time, I would like to welcome Alex and Addison to the stage so that they can present. Please hold your questions to the end. We will answer all of them together. Thank you.